So we have been talking about forces and Newton's laws, and we are going to go back to kinematics and some motion equation stuff. And the reason we looked at forces first and now we're going back is because it makes it easier to talk about some of the motion that's going on in our next unit. And our next unit is projectiles, and a projectile is just something that's being thrown or launched. And our objectives for today are to be able to identify the forces acting on a projectile in the horizontal and vertical directions, and then to be able to identify which equations of motion apply to the horizontal and vertical directions of motion for a projectile. And we're going to be specifically looking at horizontally launched projectiles for today. We will eventually move on to projectiles at an angle. So something to consider. A projectile, we have a projectile, and one easy one that's easy to kind of visualize is a projectile that's launched off a cliff. This is a horizontally launched projectile. So if a ball is thrown off a cliff, there isn't a force that's acting on the projectile in the horizontal direction after it leaves the person's hand. So this is the same thing as if a ball were rolled on a frictionless surface at 2 meters per second. In both cases, the object would continue moving at 2 meters per second forever because there isn't another force acting on it, as long as we assume there isn't any friction. Okay, so again, in space with no air resistance and no surface to rest on, the ball would go in a straight line at the same speed forever. Now, something else to consider is in the vertical direction, the only force acting on a projectile is gravity. So we still have our cliff. The only reason the projectile falls to the ground is because gravity pulls it to the ground, and that is the force that's acting on it. So therefore, in the direction of free fall, or in the vertical direction, free fall applies. So all of the stuff we learned about free fall applies in the vertical direction for projectiles. So just a kind of cheat sheet for projectile motion. When objects fall, they fall at the acceleration due to gravity. On Earth, that's 9.81 meters per second. And it should be negative. And when objects move horizontally, they continue at the same speed. That means that it's constant velocity. That means that the constant velocity equation applies in the x direction. So we usually ignore air resistance. The most that we say is, why did it slow down in the x direction? And we say because of air resistance, or why doesn't it fall at 9.81 meters per second squared down? And it's for the acceleration, we say because air resistance slows down the acceleration. And terminal velocity is when it reaches a top speed, and that's due to air resistance. So a horizontally launched projectile will continue its speed in the horizontal direction forever, while falling at a accelerated speed of 9.81 meters per second squared down. Now that forever is actually until it hits the ground. So the projectile speeds up and speeds up and speeds up in the y, and that makes it fall to the ground because it's being pulled to the ground due to gravity. And so the horizontal didn't change, but the vertical did. So the time it takes to hit the ground will be the same as a straight drop from the same height. That means, so what that's saying here is you have your cliff. The time it takes to fall like that is the same as if it went straight down. Time is the same. The time it takes to travel in the vertical direction is also the same amount of time it takes to travel in the horizontal direction. Now, this just makes sense. You may not think it does, but it has to. So it keeps traveling this way, and it stops traveling this way once it hits the ground, because then it can't move anymore. So it takes the same amount of time. Okay, so we have a practice problem. It says a plane flying horizontally at an altitude of 490 meters and having a velocity of 250 meters per second drops a supply package to a work crew on the ground. It falls freely without a parachute. What is the time required to hit the ground? How far downrange will the package travel before hitting the ground? So let's set up the problem. So we have our plane here and the package, and the package is right here. This is where it'll start falling. It has not started falling yet. So right here in the vertical direction, this initial velocity in the y, that's 0 meters per second. Now, something that I find useful is to set up an x and y chart. So this is all the motion that's going on in the x direction and all the motion that's going on in the y direction, because they act separately. The only thing that's the same is the time. So let's write down what we know. In the x direction, the velocity is going to be 250 meters per second. This is the initial velocity, the final velocity, the average velocity. In the x direction, it doesn't change. Now in the y direction, the initial velocity is going to be 0 meters per second. It has not started moving yet. You can see right here, it has not started moving. It has not started falling down yet. Then this distance right here, this is the height. This is the distance in the y. It is 490 meters. And we know that the reason it falls to the ground is due to gravity. That is an acceleration, and it's equal to a negative g, which is equal to negative 9.81 meters per second squared. Now, we chose this to be negative because the distance is going down. This must also be negative. And then we want to know the time. So time can go here, and time can go here. And we're also looking for this distance here. So this distance in the x direction. We don't know it. Now, whenever you get these problems, you will have enough information either on the x side or on the y side in order to solve for something here, usually time. And then you can go and plug time in over on the other side and solve for what you're looking for on the other side, because time is the thing. Time is the same on both sides. So to solve this, we have initial velocity, distance, acceleration, and time. That is going to be d equals VIT plus 1/2 AT squared. This initial velocity is 0. And we should follow our subscripts. So this is dy is equal to 1/2 AT squared. And then we just solve for time. So then its time is equal to the square root of 2 times dy divided by a. And we can plug in. And we end up with 9.99 seconds. That's the time it takes for it to get to these people, for them to catch it. Okay. Now on the x, we can plug this in. And the equation we use on the x side, because there isn't a force acting in the x direction, so it's a constant velocity. It's going to be velocity is equal to distance divided by time. Now you have to be careful. This distance is the distance in the x direction. It's not this one. They are not equal. So this is going to be the distance we're looking for. So we're going to solve for dx, and that's just velocity times time is equal to dx. And if we plug in, this is going to be 250 times 9.99. And that's going to be 2,498.7 meters. All right, that's what